All right, so good morning, everyone. Whether you're in person or online, I apologize for canceling class at the last minute. As you may have just heard me talking, I was chasing after a bus, fell on the road, and yeah, a little bit of blood, bruising, um, normal stuff, normal life stuff. Anyway, so I did post the videos in the playlist. Hopefully, students did, go over the video for chapter 4. But I do want to do a brief recap. Okay, so let's dive straight away into chapter 4. Chapter 4 title is Transients. Transients, so called because we are going to study the response of a capacitor or a inductor during the charging and discharging phase. Now, when we say charging and discharging, I'll explain what it means. Inductors and capacitors are energy storage devices. Okay, energy storage devices. Right, hold on. Okay. And so we have repeatedly talked about how capacitors and inductors can receive energy from a source, store it, and then release it back into the circuit at a later point in time. So this energy transfer cannot take place instantaneously, right? Cannot snap our fingers and transfer the energy into and out of these components in an instant. The energy transfer takes a finite amount of time. Now, this amount of time depends on the size of the inductor and capacitor. It depends on the energy, the amount of energy that is being transferred, and other circuit conditions. Typically, it is in the order of microseconds to milliseconds. Okay, microseconds to milliseconds. Because the capacitors and inductors we deal in regular everyday circuits are very, very small. So even though it is fleeting, it is a finite amount of time. What we will study is basically the relationship between the energy transfer during the discharge and charging phase. So when we say discharge and charging, what we are saying is when the energy is transferred to the capacitor or the inductor, we say they are being charged. And when it's coming out of the capacitor or inductor, we say they are being discharged. Okay. So if the energy is going into the components, they are being charged. If the energy is coming out of the components, they are being discharged. Because the voltage and current for a capacitor inductor are time dependent, the solution of the circuits requires solving a first order differential equation. And hence, the circuits also known as first order circuits. Typically, if you have one energy storage device, you need a first order differential equation. So it's a first order circuit. If you have two energy storage devices, it's a second order circuit, and so on and so forth. Typically, we can combine multiple inductors together to form one inductor, multiple capacitors together to form one capacitor. And so we can have first order circuits, even though physically we may have multiple capacitors and inductors. Okay, so analysis of the circuits during the phases is transient analysis. There are 4 kinds of circuits, depending on whether they are being charged or discharged. And the response of these circuits are known as natural response or step response. The word forced has sinister connotations, but it's not sinister. Forced simply means that the response of the circuit, meaning the voltage and current that appears in the circuit, is not due to any stored energy. Okay, if it's a stored energy, meaning there is no source connected in the circuit, we call it it's a natural response. Forced response is basically you connect a source to the circuit. So source connected, we call it a forced or a step response. and no source connected is a natural response. Okay, natural response. Now, depending on whether it's natural or forced, we have 4 different kinds of circuits. We have RL and RC for discharge, and we have RL and RC again for charging. Now the chapter goes through, and if you have already looked at the videos, then you'll see there is a derivation for each one of these circuits. But as I said, I will do a recap. And in this recap, I'm going to talk about one single equation that can be used for all kinds of circuits. So this is the one equation to rule them all. And I'll explain each and every component quantity of this equation. X of t is equal to x of f plus x0 minus xf into e raised to minus t over tau. This tau is the Greek letter tau, is known as the time constant of the circuit. So let's take it one quantity at a time. First, what is it that this equation is describing? Is x of t. X of t. X can be either voltage or current. Okay, X is either voltage or current. Typically, we write the current equation for an inductor, and we write the voltage equation for a capacitor. Okay, so X can be either current or can be voltage for both inductor and capacitor. For an inductor, we typically write the current equation first. For a capacitor, we typically write the voltage equation first. The of t simply means that the quantity is a function of time. The value of the voltage or current would take on any value depending on the time, right? The voltage or current for the inductor or the capacitor during this charging or discharging phase is a function of time. So x of t is simply the voltage or current for the inductor or capacitor as a function of time. At any given point in time, value is different. So that's the first thing. X of t is describing the voltage or current as a function of time. So x can be either v or can be I. Then if you look at this equation, you have the subscript f and 0. Okay, f and 0. F simply indicates final conditions. 0 is the point in time where we begin our analysis. So it's describing the initial conditions. Okay, initial conditions. It's the starting point. So F is the end point. 0 or I is the starting point. Again, remember, we're talking about charging and discharging of circuits. So there is a starting point and there's an end point for both. At this point, I've been talking nonstop, so let me take a pause and you can ask any questions that you may have. All right, any questions from anyone? Okay. All right, so F is the end point, 0 indicates the start point of the analysis. For a charging waveform, let's start with discharging. For a discharging waveform, time is always on the x-axis, and this could be V or I. If you're discharging, doesn't matter where you start, your end point is always zero. Whether it's 0 volts or 0 amps. But for a discharging circuit, a discharging analysis, your end point will always have a value of 0. So XF for a discharging circuit will always be 0. Okay, so XF will always be 0. If it's a discharging, it doesn't matter if the discharging gets interrupted in the middle, which is something you will see in the lab today. If the discharge gets interrupted in the middle, it doesn't matter. As long as you are analyzing that portion of the circuit for discharging, your end point is always 0. So XF is always 0. The only thing in that equation that remains is X0. Does that make sense to everyone? Right? The only thing that remains in the circuit is X0. Now, if you are charging, your final value, XF, would be at a point that might be equal to the source if it's connected directly, or it would be equal to the voltage that would appear across those terminals, which would be the Thevenin voltage or the Norton current. So it depends on the source voltage or the source current, and then as seen by the component. So VTH or IN. Now in the quiz or an exam, I'm not going to give you like a large circuit and ask you to, figure it out yourselves. It'll be part of a larger circuit, but you will already know the value because you would have already calculated the Thevenin voltage or the Norton current. And that would be applied to the component. Starting point, X0 here. X0 could be anything. It could be 0 if it's not mentioned, or it could be the initial stored energy in the component. Okay, so it could be 0, or it could be the initial stored energy in the component. If the value is given, you take X0 as the initial stored energy, the value. If it's not given, then you assume it to be 0. Okay, if it's not given, you assume X0 to be 0. So those are your two values, the initial start point and the final end point, X0 and XF. Then is the last quantity, E raised to minus T over tau. E is, of course, describing the exponential relationship that the voltage or current has with respect to time. Okay, so E is describing the exponential relationship. And you notice both these waveforms, whether it's charging or discharging, have an exponential relationship with time. Then E raised to minus T over tau describes the charging or discharge speed. Or actually, tau describes the charging or discharging speed. T is, of course, the variable, and tau is a constant. And it's a constant that depends on the values of the components in the circuit. Okay, it is describing the rate. It is describing the rate of flow of energy. It is describing the speed of the energy transfer. How fast or slow is the energy being transferred between the circuit and the components. So for a RL circuit, meaning an inductive circuit, it is L divided by R. For a RC circuit, it is simply the product of R and C. Okay. So tau for a RL circuit is L divided by R. For a RC circuit, it is R times C. Yes. Yes. So in the homework, there are circuits for both inductors and capacitors. In the chapter also are the examples. And so in the videos that are already posted, I cover all three examples. I think two of them are for inductors and one is for capacitor. So you have three quantities to find. You have R, you have capacitor. So you have resistance, capacitance, and inductance. You can calculate tau directly. You determine the starting position and the end point, and you directly plug in those values into this equation, and that's it. That's the solution to the circuit. That's the solution to the voltage or the current for the charging or discharging phase. Okay, as straightforward as that. You have only, the equation seems more involved, but there's only three components: XF, X0, XF, and tau. The start point, the end point, and the rate of the energy transfer. Those are the only three things you need. And if it's a discharging problem, then XF is always, always, always 0. Then you need only two things: tau and X0. That's it. X0 is the starting point, and tau is dependent on the physical values of the physical components. All right, questions? Any questions? Have you all looked at the videos that I posted? Hopefully some of you did. Some of you didn't. And of course, this will also be on there. Again, it's, as I said, missing that one. I tried not to miss it, but I was like not even able to stand properly on that day. So yeah. But yeah, that's 2 hours, and that's 2 hours is usually what I devote to the entire chapter, the examples. So go over the examples in the videos, again, in the interest of, of students being able to ask direct questions. I wanted to devote 20 minutes of today's class to go over this equation so that students can answer questions directly. Homework 13 based on this chapter was due, was it homework 13 or 14 was due on Saturday. But again, if students have lost any points or anything, I'll extend the homework deadlines and I'll make sure students don't lose any points. So just get the homework done. Whenever you get done, I'll adjust the points. Okay. And I also have to, I've caught up with the other homework assignments. I do need to adjust the grades for the first week assignment. So whoever emailed me, I will get to it sometime this week. And then the quiz 1 is done, and then quiz 2, 3, 4, 5 is something I want to get done in the next few days. So then we'll be all caught up on your grades. Okay. Any questions? Okay, then I want to get started with chapter 5. Chapter 5 is AC analysis. AC analysis. The name sinusoidal comes from the fact that most of the analysis relates to the sinusoidal waveform that looks like this. Okay. This entire chapter is basically about AC. Okay. So what we're going to study in this is how do AC circuit works compared to DC. What roles do the three components play in these AC circuits? What roles do they have? And how can we mathematically model the relationship of these components and the voltage and currents in these components in response to an AC source. So the first thing I would like to point out that what makes this AC circuit or an AC analysis is basically the source. The components are still the same. Resistors, inductors, and capacitors are still the same. There is no difference. But what makes it an AC circuit is the source. So if the source is AC, meaning alternating, then we refer to it as an AC circuit. Okay. And here are some examples of AC waveforms. Now, when we say waveforms, we are simply stating a graphical illustration, an image and picture of the value of the voltage or current with respect to time. The time will always be on the x-axis. Okay. X-axis will always be time in seconds. You have to pay close attention to the units because units could sometimes be seconds, it could be milliseconds, it could be microseconds. So always pay close attention to the units in the waveform. So again, waveform is a graphical illustration of the voltage or current with respect to time. Y-axis could be either voltage or current or power. Okay, V or I or even power P as a function of time. Similar to chapter 3, we can write it simply as V or V of T. Okay, the of T is sometimes just understood or implied. Okay, so if we have a AC circuit, logic dictates that the voltage or current would be a function of time. So sometimes the T would be omitted. Okay, so it could be V of T, could be I or I of T. Sometimes it would be P or P of T. Okay, so sometimes the T could be omitted. This right here is a sinusoidal waveform. The sinusoidal waveform is so called because mathematically we can represent it using the sine or the cosine function. Okay, basically any voltage or current, any quantity that has a varying relationship with time is referred to as AC. This is different from the response that we studied in the previous chapter. Okay, transient response, we said has, it is a nonlinear relationship with time, but that is different. This is different. This is a source where the source has a constantly changing value. As a real life example, this microphone that I'm wearing right now is capturing the sound waves and converting it into electrical signals. The electrical signal, if I plot it or observe it on an oscilloscope, would look something like this. And depending on how high or low my voice goes, the electrical signal will change the frequency and the amplitude. Okay, so if I make a loud noise, the amplitude or the Y direction might change. If I change the tone of my voice, whether I go very high squeaky or go very deep like a baritone, then the frequency on the x-axis would change. Okay, and we look at what each of these terms would mean. Basically, any quantity that changes its value with respect to time is AC. Here are some of the other more common ones that we use: triangular, square, rectangular, and a sawtooth or ramp waveform. Each one of these has their own functions. Some of these are very specialized. The rectangular and square waveforms, primarily used in digital, where you either have it on or off. On is basically where the waveform has a value. Off is where the value is 0. So all digital logic circuits are based on square and rectangular pulses. It's either on or off, meaning it's either 0 or 1. Okay, let's take a pause. Let me know if you have any questions at this point. Any questions from anyone? So we will primarily be working with sinusoidal waveforms. Okay, sinusoidal waveforms, because AC is very easy to generate. It's very easy to distribute. Everything that we use in everyday life is based on the sinusoidal waveforms. Okay. If you recall from the first week of classes where I talked about AC versus DC, and I stated the power outlet rating, you have voltage, you have frequency. What is the voltage rating of the standard power outlet in North America? Anyone remember? It's going to be on the final exam. The voltage, 120. So it's between 110 to 120 volts. Sometimes it fluctuates depending on the time of day. There's heavy load, voltage might drop a little bit. What is the frequency? Anyone remember? So in North America, the voltage is between 110 to 120 volts, and the frequency is 60 hertz. Any appliance that you plug into a wall outlet, would have this information on a label somewhere on the device. If you plug in your laptop adapters, your smartphone chargers, your tablet chargers, somewhere in there, there's a small sticker with very tiny letters that you will still be able to read with your young eyes that states 100 volts to 240 volts, meaning you could use that device anywhere in the world, electrically speaking. Physically, the prongs are different. North America has flat prongs. Europe and Asia, they have these round prongs. So you might need to get a physical adapter, but you would not need to get an electrical adapter. You could take your laptop chargers and just plug it anywhere in the world just by applying a physical adapter. So again, take a look at the laptop adapters and your smartphone chargers, and we'll have this voltage rating. What it means is the 60 hertz and the 110 volts or 120 volts, we'll go into the technical details in just a bit. Okay, but what it actually means is it changes its value and fluctuates between these values a set number of times in one single minute or in one single second. Okay, now the mathematical description of a sinusoidal waveform is given by this equation. V of t is Vm cos of omega t plus or minus theta. Okay, I say plus or minus because theta can take on a value positive or negative. Okay, positive or negative. This equation works for voltage, current, or power. They all have this exact same equation. So V of t, I of t, at any given point in time, okay, t can take on any value, 0, 1, 2, 3, or 0, 0.1, 0.2, 0.3, any value. And this equation would describe the value of the voltage or the current at that point in time. Does that make sense? V of t is given by Vm cos of omega t plus theta. Three quantities, Vm, omega, and theta. And look at each one of those individually in the next few slides. But this is the standard expression that we'll look at for the entire chapter, actually even going beyond this chapter. So this is the most important. And this is the point in time where I ask students if you can perform complex math equation or complex math on your own calculator devices. This is also the purpose of asking students to not relate, but to post about the calculators that you're using, because you need peer support if you don't know how to perform these operations. Okay, so we'll work with complex numbers to make the math less complex. And I will come back to these after we look at each one of these quantities in detail. Let's start with Vm first. Okay, the M stands for magnitude. It basically describes the value of that quantity on the y-axis. Okay, it describes the quantity, value of the quantity on the y-axis. So x-axis is always time, y-axis values, which is voltage or current or power, is described by the magnitude, or also known as the amplitude, or also known as the peak values. So they can be described as Vm or Vp. P stands for peak. Similarly, if the equation was describing a current, it would be Im or Ip. And that peak or magnitude is basically this max value in the y direction. So this, the waveform is red. In red is 0.5. Waveform in black has a value of 1. Waveform in blue has a value of 2. So all waveforms have a similar shape and the same frequency, but the y-axis values are different. The maximum value of that peak right here is described. This is described by this term right here, Vm. Okay, Vm. Let's take a pause, think over it, and let me know if you have any questions. Any questions so far? Okay, so Vm is describing the peak. What do you notice? What do you notice? It's only describing one peak, not both. Okay, it is only describing one peak. It is not describing both. So Vm or Vp describes one peak. The assumption is that the waveform is symmetrical around the x-axis. Okay, the waveform is symmetrical around the x-axis, so it's describing one peak. So the actual waveform goes from peak to peak, where P dash P is describing both peaks. Peak to peak, okay? Peak to peak. So the waveform is describing both peaks. Does that make sense? Okay. All right, then let's talk about frequency. Frequency is noted by lowercase f. It basically is telling you how frequently the waveform cycles through a positive and a negative peak in 1 second. Okay, so a waveform starts at 0 goes to its positive peak, so plus VP or plus VM. And now I'm just using the voltage V to describe this, but it applies equally to I also, okay? Goes back to 0, goes negative, and then comes back up to 0. And this is minus VP or minus VM, okay? This is referred to as one cycle. One cycle, okay? Where it starts from 0, goes to a positive peak, goes to negative peak, comes back to 0. So it's one cycle. And the number of cycles that a waveform completes in 1 second is termed as the frequency of the waveform. Okay, it's termed as the frequency of the waveform. So the number of cycles the waveform completes in 1 second is termed as the frequency of the waveform. So 60 hertz frequency for our power outlet indicates that the waveform goes positive, negative, positive, negative 60 times in 1 second. At some point, the waveform has, at some point, that waveform starts from 0, has a value of 0, goes up, comes back to 0, goes negative, comes back up to 0. 60 times in 1 second, well, actually 120 times in 1 second, the waveform has a value of 0. So if you were Dr. Strange and had the power to slow down time, and you stick your finger in the wall, you would feel it going up, down, up, down. But thankfully, I think none of you have the power to slow down time, and none of you are probably Dr. Strange, so don't stick your finger in the wall. Don't stick your finger in the wall. All right. Questions? The frequency is so high. So the question being asked is the safety feature to keep the frequency high? No. And that also leads me into my next point, which is a 60 hertz frequency seems very high to us, but in real life, 60 hertz is very, 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 very low frequency. And I'll illustrate by an example. We all have wireless routers in our homes, in workplaces. What is the frequency of these wireless routers? You would have heard dual band wireless routers nowadays. The frequency of a standard wireless router is 2.4 gigahertz. The other band of the wireless router is 5 gigahertz. You remember giga from that table in chapter 1? How much is it? As engineers, as I stated then, I don't expect everyone to memorize all of the values, but some of the values in the middle we should. So we start with kilo, which is 10 raised to 3, mega, which is 10 raised to 6, then comes giga, then comes tera, and then peta, exa, and so forth. But so gigahertz is 10 raised to 9. Insanely high value, but very common in electrical engineering. AM radio stations are broadcast at a frequency of kilohertz. FM radio stations broadcast at a frequency of megahertz. So kilo is 10 raised to 3, mega is 10 raised to 6, and then we have terahertz 10 raised to 9. So megahertz, 680 kilohertz, 680 AM, meaning the radio station is broadcasting at a frequency of 680 kilohertz, Even in broadcast communications, that is considered to be the low end of frequencies. So low is relative, obviously. The highest human hearing range would be in about 15, 16 kilohertz, right? So anything above 20 kilohertz, humans cannot even hear. So for us humans, 15, 16 kilohertz is a high value. Whereas for broadcast AM radio stations, 680 is the standard. So 20 kilohertz is far lower than their spectrum. So again, low and high is relative. 60 hertz power outlet, in generally speaking, is a very low frequency, but for us humans, it's high because 60 times in 1 second. Make sense? Here are some examples, of course, of how frequency changes. So x-axis, as I stated, was time. Frequency is basically the number of cycles in 1 second. So it has the exact opposite or inverse relationship with time. Uppercase T is noted as the time period of the waveform, meaning 1 cycle. Okay, 1 cycle. So you take the inverse of 60 hertz, 1/60, and that value in seconds is the time period of the waveform of the power outlet. Okay, that's what it is. Then let's see. Then at this point, I would go back to this slide right here and I would explain what the omega is. Okay. So I said, we talked about the frequency, lowercase frequency, lowercase f notes frequency, and the unit is hertz, or more commonly known by its acronym, uppercase H, lowercase z. Not the car company. It's named after a German physicist, Hertz. And T, of course, is in seconds. And omega is the angular frequency or the angular velocity given by the equation 2 pi times f. Because we will model this as a rotating vector. So like a circle. Okay, we'll model the sinusoidal waveform as a rotating circle. So 2 pi basically is noting 1 full circle, 360 degrees. And omega, as I stated, is the angular frequency. It is defined or not defined, described by the units radians per second. Radians per second. Okay, it's 2 pi radians makes 1 full circle, hence radians per second. All right, that's a lot of terms, a lot of units. So think over that. Let me know if you have any questions. Any questions so far? Are we clear on the magnitude or the amplitude? Yes. If students learned this, the question being asked is this the same? Is this the same as we learned in physics 2? The answer is yes. It would not change. So if students have already learned this in physics 2, consider this as a refresher. If you have not learned it, then well, yeah, it's the same stuff. One thing I wanted to point out again was the book and the system uses the acronym M, but more commonly it is known as P. So if you operate an instrument, instead of M, the instrument would say P. Other books, other authors, other systems would use P. They both mean exactly the same thing. They're describing the y-axis value of that quantity. Okay, so it's VM or VP or IM or IP. Our book and our Pearson system uses M, but most systems use P. Okay, so remember this fact. It's the y-axis value of the quantity. Okay, then finally, we describe the phase. Now, the phase is described in degrees. There is a reason we do that. Okay, and the reason will become clear when we go to the phasor transform. This phase angle obviously can be described in radians, and we can combine it with the omega value, but we don't do it. We keep it separate because there's a mathematical purpose to it. So we describe that phase in degrees. And what that phase describes is basically the point in time where the waveform crosses the x-axis. Basically, where is the zero value of the waveform? Okay. So if you look at the waveform in black here, there is no phase. Basically, it is 0 degrees, right? It is 0 degrees. It is plus minus 0. It is basically telling us that the waveform in black crosses the x-axis when t is equal to 0. Okay. It is crossing the x-axis when t is equal to 0. This, of course, indicates time t equal to 0. Time t equal to 0, right? Now, ignore the pi and the 2 pi listed here, okay? That's the x-axis values in radians. But if this was in seconds, if time is in seconds, what are the values on the right side and what are the values on the left side? You have positive values on the right, correct? +1, +2, +3, and so on and so forth. On the left, you have -1, -2, -3, and so on and so forth. So if time is 0, meaning this is the beginning of your analysis, what does +1, +2, +3 indicate with respect to time? Logically speaking, if you begin your analysis at 0, what does +1, +2, +3 indicate? It's going to come in the future, right? So t is equal to 0 is when we begin our analysis. +1 is the moment that is going to come after our analysis. So everything on the right is the future. Everything on the left is the past. Does that make sense? +1, +2, +3, everything on the right, meaning it is yet to come. T is equal to 0 is when we began our analysis. Positive values, or the right side of the waveform, is indicating the moments that are yet to come. Everything on the left side, the negative values, is basically the time that has already gone by. It is ahead. So moments in time or phase that is negative, so on the left side, it is showing, sorry, not phase that is negative. The moments on the left side is indicating the past, meaning it is ahead in time. It is already gone by. Everything on the right is the future. It is yet to come. And so the phase is indicating the point either in the past or in the future. But the mathematical notation is exactly the opposite. Okay, so be careful about this. Time is +1, +2, +3, positive values on the right. However, if your waveform is on the right, it is behind the waveform that is already ahead of it. So if you look at the black and the red waveforms for now, the black waveform has 0 degrees of phase. because it is crossing the x-axis exactly at time t equal to 0. The value of the waveform in black has a value of 0 at time equal to 0. Does everybody see that? Right? Has a value of 0. Magnitude is 0 at time t equal to 0. However, at time t equal to 0, the waveform in red has not yet arrived. It has a value negative 0.5. Okay. So we can say the waveform in red is behind the waveform in black. And the distance between the two is described by this phase. And because it is behind in terms of time, we note it with a negative value. So even though it falls on the positive side of the y-axis, it is still mathematically described with a negative value. The phase is negative with respect to the waveform in black. So think over that. Let me know if you have any questions. I'll just talk about the positive phase and then we'll take a break. So positive phase, similarly, the waveform in blue is on the left side of the waveform in black, meaning it has already arrived before the waveform in black arrived. So if I, let's say, A, B, C, waveform in blue is A, waveform in black is B, waveform in red is C. So A has already gone by. It is already ahead of B, and A and B are both ahead of C. Make sense? And so we note that with a positive phase angle. So even though it falls on the negative side, we note it with a positive phase. So if the waveform is ahead, it is positive. If the waveform is behind, it is negative. And that is the mathematical notation for these two waveforms. Okay, and so that's where all these values come from. Cos omega t plus or minus theta. And theta is kept separate in degrees. Omega is in radians per second. This is in degrees. And this, of course, if it's voltage, it's in volts. If it's current, it's in amps. Okay. If it's IM, then it's amps. And I've pointed the same thing out here in this slide, right? Volts, radians per second, and degrees. Now, the entire expression is describing voltage as a function of time. So we don't have to note the units individually. If we are describing V of t, the overarching units for the entire expression is simply volts V. Okay. If it was I of t, then you'd have amps or A at the end. That's how we would note the units. All right. So it's 11:05. I think it's a good time to take a break. Let's take a 5-minute break and we'll pick up again at 11:10.